Welcome to the Whispering Scientist, where the day's sharp edges soften and the universe reveals its quieter truths. This is your refuge from the noise, a gentle harbor where curiosity meets calm and the cosmos takes on a more patient voice. Whether you found your way here from a restless evening, tucked beneath soft lamplight, or simply drawn by the desire to drift alongside the stars, you're exactly where you need to be. I like to picture you as a small island of calm, and others listening from their own quiet shores too. Little lights scattered across continents and oceans, all sharing this same slow moment beneath different skies. Before we begin tonight's gentle journey, I'm always curious about something that fascinates me. Where in the world are you listening from? It's extraordinary to imagine this same stillness stretching across time zones, connecting listeners beneath the northern lights, city windows, or perhaps where the Milky Way still shows itself clearly. Wherever you are, you're part of something larger, a constellation of minds that finds peace in understanding. If you're new to this corner of the evening, a gentle reminder that your support truly helps the Whispering Scientist grow, reaching more sleepy minds who enjoy drifting off to the rhythm of science. A simple like and subscribe mean more than you might realize. For those already part of this little community, thank you. Your quiet presence here anchors these explorations. Don't forget to tap that notification bell if you'd like, so when the next peaceful journey begins, it can find you easily. I do hope tonight's exploration isn't so fascinating that it keeps you awake, but if it does, at least you'll fall asleep a little wiser than before. So let's begin softly with a question that seems almost impossible when you first hear it, yet touches every moment of your existence. Why does space bend? What does it even mean for the invisible stage of reality to curve like a hillside or flex like fabric? For as long as humans have watched the night sky, we've seen motion everywhere. The moon glides across its dark sea of stars. Planets trace their silent, predictable patterns. The stars themselves seem fixed, eternal. Yet we know they too are dancing in patterns too vast and slow for human lifetimes to perceive. For most of history, this cosmic choreography was explained by invisible pulls, mysterious attractions reaching across the emptiness between worlds. It worked beautifully. With the right mathematics, you could predict where Mars would be in 100 years, when the next eclipse would darken the sun, how fast a stone would fall from a tower. The universe seemed to run on invisible strings, each object tugging on every other object across infinite space. It was a vision of harmony written in equations, a clockwork cosmos where every motion had its cause. But as our instruments grew more precise, something curious began to emerge from the observations. Every object, from the smallest pebble to the largest planet, seemed to fall in exactly the same way. A hammer and a feather, if you could somehow remove the air between them, would strike the ground at precisely the same moment. A cannonball and a coin dropped from the same height would trace identical paths through the air. This wasn't just a curious coincidence. It was a clue written in the language of falling things that something deeper was at work. Why would gravity treat everything so democratically? Why would objects of vastly different weights and compositions all respond to this invisible pull in exactly the same way? And even more puzzling, why would light, which has no weight at all, bend around a massive star as if it too were following a path set out for it by the cosmos itself? In the early 1900s, this quiet puzzle began to stir a revolution. A young patent clerk working in Switzerland, a man named Albert Einstein, dared to suggest an entirely new way of seeing. He proposed that gravity might not be a force pulling downward, but rather a profound change in the very shape of space and time themselves. His famous insight, both simple and revolutionary, can be distilled into one elegant sentence: matter tells space how to curve, and space tells matter how to move. It was a statement so deceptively straightforward that it concealed an entirely new vision of reality. one that would transform our understanding of how planets orbit, how starlight travels, and even how time itself flows. Tonight, we'll drift gently through that curved fabric, exploring how this subtle bending creates everything we experience as gravity. We'll discover how falling can be a form of freedom, how clocks run at different rhythms depending on where they sit in the cosmos, how light itself takes graceful detours around stars, and even how space can ring like a bell when great masses collide in the deep reaches of the universe. There's no rush on this journey, no complex mathematics to decipher, and absolutely no pressure to remember anything. Just allow these ideas to unfold slowly, like distant constellations forming in the dark expanse of night. By the end, the cosmos may feel a little less like a place of invisible forces and more like a profound poem written in the elegant language of geometry. So settle in, let your shoulders lower half an inch, and allow the night to get a fraction deeper. The universe has been patient with its secrets for billions of years. It can wait a little longer while you find your own pace through its gentle mysteries. Before we learn how space bends, though, it helps to remember how we used to think about motion, in the language that first tamed the sky for us. Before we learn how space bends, it helps to return to the language that first tamed the sky for us. The elegant mathematics that let sailors trust their charts and astronomers trust their telescopes. In that earlier music of the universe, Sir Isaac Newton wrote a score so clear and powerful that the motions of apples and moons could be described by the same gentle notes. He looked up at the planets gliding along their graceful ellipses and down at a stone leaving a hand, and he dared to say they were part of a single, invisible symphony. Gravity, in Newton's telling, was a steady, universal pull that every bit of matter exerts on every other bit, weakening with distance but never quite reaching zero. The rule was simple enough to write compactly, yet its consequences rippled through everything we could observe. With it, the arc of a cannonball and the orbit of Jupiter became chapters of the same cosmic story, connected by threads of mathematical harmony that stretched across the solar system. This was an astonishing act of unification that brought peace to centuries of celestial mystery. For generations before Newton, astronomers like Johannes Kepler had mapped the geometric poetry of planetary motion, discovering ellipses and harmonies without understanding their cause. Newton supplied that missing cause. He showed that an invisible pull, combined with motion already in progress, would naturally sculpt those elegant orbital shapes. Suddenly, engineers could build bridges with confidence. Navigators could cross oceans guided by clockwork predictions, and astronomers could forecast exactly when wandering comets would return from the outer darkness. What made Newton's vision so deeply satisfying was its democratic universality. No special rules divided heaven and earth, no separate physics governed stars and stones. The same equation that described a pebble falling from a windowsill could chart the moon's monthly journey around Earth. Tides, eclipses, the subtle bulge of our spinning planet, even the wobble of tops and gyroscopes, all became intelligible through this single, elegant principle. You could picture the solar system as a graceful balance, the sun's inward pull matched against each planet's forward motion. Every orbit a gentle compromise between falling and flying. For over 200 years, this clockwork cosmos ticked forward with mechanical perfection. If you knew the masses and distances involved, Newton's equations promised you could predict the cosmic future itself. The moon would be exactly where the mathematics said it would be, not just tomorrow, but 1,000 years from now. It felt complete, reliable, almost comfortingly predictable. And yet, even within this beautiful music, a few quiet notes refused to settle into harmony. Newton himself heard them clearly. With a rare humility for such a towering genius, he admitted he did not know how gravity's pulling actually happened. He called it action at a distance, a force that seemed to leap invisibly across emptiness with no apparent mechanism. How did Earth somehow reach across nearly 400,000 kilometers of apparent void to tug on the moon? What invisible thread connected them with no rope, no wind, no signal to carry the gravitational message? In his private correspondence, Newton was deeply troubled by this gap in understanding. He wrote that the idea of one body acting upon another through empty space without the mediation of anything else was so great an absurdity that I believe no man who has, in philosophical matters, a competent faculty of thinking can ever fall into it. Yet his equations worked so perfectly that most people simply accepted the mystery as part of nature's fundamental design. The predictions fit reality so beautifully that few questioned the mechanism behind the mathematical magic. There was another whisper too, faint but persistent, emerging from the way things fell. Every object, regardless of its weight, shape, or composition, fell in exactly the same way. A hammer and a feather, if you could remove air resistance, would strike the ground with perfect synchronization. A cannonball and a coin, dropped from the same height, would trace identical paths through space. This wasn't mere coincidence or approximation. It was a precise, universal truth that seemed to hint at something deeper. In Newton's framework, the strength of gravity's pull on an object was proportional to its mass, while the object's resistance to acceleration was also proportional to its mass. Two different masses playing different roles, yet in every experiment they cancelled perfectly. Why would heavy and light things move identically if gravity was simply a pull proportional to mass? This exact equality had the flavor of a coincidence that refused to admit it was one, quietly suggesting that everything was following the same natural path through space and time. As centuries passed and instruments grew more sensitive, small but persistent cracks began appearing in Newton's grand clockwork. The most famous emerged from Mercury, the innermost planet racing swiftly near the Sun. Precise measurements revealed that Mercury's elliptical orbit wasn't quite closing on itself. Each time around, the planet's point of closest approach to the Sun crept forward by a tiny amount, causing the entire ellipse to slowly rotate like the petals of a turning flower. Most of this precession could be explained by gravitational tugs from other planets, but even after accounting for every known influence, a small remainder persisted. 43 arc seconds per century, barely perceptible yet unmistakably real, a subtle drift that Newton's equations couldn't quite capture. It was a minute discrepancy, no more than the width of a hair seen from across a football field, but it was reproducible and precise. Something about the way gravity worked near the Sun wasn't fully described by the old, reliable rules. Meanwhile, new discoveries about light and energy were beginning to reshape physics in unexpected ways, suggesting that the universe was far more dynamic and interconnected than anyone had imagined. The puzzle pieces were quietly arranging themselves, waiting for someone to see the hidden pattern within them. The democratic nature of falling objects, the mysterious mechanism of action at a distance, the subtle anomalies in planetary motion, all pointed toward a deeper truth about the nature of space, time, and gravity itself. What was needed was a mind willing to question not just how gravity worked, but what gravity actually was. That revolutionary perspective would soon emerge from the most unexpected place, transforming our understanding of the cosmos in ways that Newton, for all his genius, could never have imagined. That revolutionary perspective would soon emerge from the most unexpected place, not from a grand observatory or towering equations, but from a simple image that drifted through the mind of a young patent clerk in Switzerland. Albert Einstein, sitting quietly in his office in 1907, began to picture something so ordinary it seemed almost trivial. Yet within this gentle thought lay the key to understanding the deepest architecture of reality itself. Imagine yourself standing inside a small, windowless room floating somewhere in the vast emptiness of deep space, far beyond the reach of any star or planet, where even the faintest whisper of gravity has faded to nothing. You release a set of keys from your hand, and they simply drift beside you in perfect stillness. There's no sense of up or down, no pressure against your feet, no weight in your shoulders. just the soft hum of absolute nothingness, the serene suspension of existing where motion has no preferred direction. This, Einstein realized, was what the true absence of gravity felt like. Not falling, not being pushed or pulled, but floating in the gentle embrace of emptiness itself. But then his imagination took the most curious turn. He pictured that same sealed room, identical in every detail, except now it wasn't drifting peacefully through space. Instead, the cables had been cut, and it was plummeting freely toward the surface of Earth. And here was the remarkable thing that would change our understanding of the universe forever. Inside that falling chamber, you would feel exactly the same weightless serenity. You would release those same keys and they would float beside you just as peacefully. Your feet would feel no pressure from the floor. Your arms would move with the same effortless grace. And every gentle experiment you could perform would yield identical results. This wasn't because gravity had mysteriously disappeared. The room, you, the keys, the very air around you were all accelerating downward together at precisely the same rate, creating a perfect bubble of apparent weightlessness. Everything was falling as one harmonious unit, following the same natural path through space and time. To you, sealed inside with no windows to reveal your motion, the experience would be utterly indistinguishable from drifting in the peaceful depths of space. Einstein called this profound realization the equivalence principle, and though it sounds almost too simple to matter, it contained the seed of an entirely new vision of gravity. He later described the moment of understanding as the happiest thought of my life. If falling freely in a gravitational field felt exactly the same as floating weightless through empty space, then perhaps these two situations weren't just similar, they were fundamentally identical. Maybe what we call gravity isn't a mysterious force reaching across space to pull on objects at all, but simply the natural motion that everything follows when left completely undisturbed. This insight gently turned our everyday understanding upside down in the most elegant way imaginable. What you feel as weight when you stand on solid ground isn't gravity itself acting on your body. It's resistance. The floor beneath your feet is preventing you from following your natural preferred path through the fabric of space and time. When you're standing still, it's actually the Earth's surface that's pushing up against you, not some invisible hand pulling you down. The sensation of weight comes from being denied the freedom to fall, from having your natural motion interrupted by the solid world around you. Consider an astronaut floating serenely inside the International Space Station, orbiting high above our planet. From our perspective on the ground, they appear to be constantly falling toward Earth, racing around it at tremendous speed to avoid crashing into the surface. But from their own quiet perspective inside the spacecraft, they're simply drifting in perfect tranquility. They're not fighting against gravity or being held up by anything at all. They're following the most natural path available to them through the curved geometry that surrounds Earth, falling freely and perpetually, never hitting the ground because the planet's surface keeps curving away beneath them at just the right rate. The same principle illuminates why all objects fall at exactly the same rate, regardless of their mass or composition. They're not being pulled by some force that somehow treats everything equally. Instead, they're all following the same geometric path through space and time, tracing the straightest possible route through whatever invisible landscape surrounds them. A feather and a hammer fall together on the moon, not because some mysterious force treats them identically, but because they're both moving along the same natural trajectory through the fabric of reality itself. Einstein's falling elevator also explained why acceleration and gravity feel so remarkably similar. When you're pressed back into your seat during an aircraft's takeoff, you're experiencing the precise opposite of free fall. The engines are pushing you upward, while your body naturally wants to continue along its original path. That sensation of weight comes from resistance to your preferred motion, just like standing on solid ground. The push is what you feel, not any downward pull. Once Einstein grasped this deep equivalence between falling and floating, between acceleration and gravity, he realized it couldn't possibly be mere coincidence. It pointed toward a profound truth about the nature of space and time themselves. If you could always find a freely falling reference frame where the laws of physics looked exactly the same as they did in empty space, then gravity must be something far more fundamental than a simple force. It must be woven into the very structure of reality, written into the geometry of existence itself. This led to an extraordinary conclusion that would reshape our understanding of the cosmos. In small enough regions of space and time, you could always find a perspective where gravity seemed to vanish entirely, where the universe felt perfectly flat and simple. But this illusion only worked locally, in your immediate neighborhood. The magic broke down when you looked across larger distances, where subtle differences would begin to appear, hinting at a deeper curvature that shaped the paths of everything from falling apples to orbiting planets. What Einstein had discovered was that space and time weren't separate, static stages where things happened. They formed a single, dynamic fabric that could bend and flex, creating invisible landscapes of hills and valleys. And it was time to explore how these two fundamental aspects of reality had been partners in the same cosmic dance all along. What Einstein had discovered in his falling elevator was that space and time weren't separate, static stages where things happened. They formed a single, dynamic fabric that could bend and flex, creating invisible landscapes of hills and valleys. And it was time to explore how these two fundamental aspects of reality had been partners in the same cosmic dance all along, woven together so intimately that you could never truly speak of one without the other. If space was simply a three-dimensional stage where events unfolded, and time were merely a ticking clock keeping score in the background, the universe would be far easier to picture. Our minds, shaped by everyday experience, naturally want to separate these concepts. We speak of where something is and when something happens as distinct pieces of information. But the truth Einstein uncovered was both stranger and more elegant than anyone had dared imagine. Space and time are threads of the same cloth, so intertwined that pulling on one inevitably moves the other. Compress time and space stretches in response. Twist space and time bends along with it. This unified entity, which physicists call spacetime, isn't just the backdrop for cosmic events. It's the stage, the script, and the motion, all woven into one seamless tapestry. To understand why this unity is so profound, think about how we describe any event that happens in the universe. Whether it's a supernova exploding in a distant galaxy, a raindrop striking your window, or the simple act of you settling deeper into your pillow, every occurrence can only be pinpointed when we know both where and when it took place. A location alone tells us nothing meaningful. If you say the moon, that description is useless unless you also specify when the moon was there, because it's constantly gliding through space, tracing its monthly path around Earth like a silver boat on an invisible river. Time, then, is the fourth coordinate that makes every moment in the universe unique and complete. Together, the three dimensions of space and the single dimension of time give every event its full address in the cosmic web. This seemingly simple idea that where and when are inseparable was what led Einstein to unite space and time into a single, coherent structure that describes reality more completely than either could alone. The remarkable thing is that you experience this unity every moment of your existence, even as you listen to these words. When you move through space, you're also traveling through time, but in a way that's far more subtle than you might expect. If you lie perfectly still, you're moving through time at a steady rate, one gentle second per second, drifting forward into the future like a leaf on a slow river. But when you shift position, when you walk to the kitchen or turn your head on the pillow, something beautiful and almost magical happens. A tiny portion of that forward motion through time gets traded for motion through space. You don't notice this cosmic exchange because the speed of light, which sets the conversion rate, is so vast that your human share of it is utterly minuscule. But the trade is there nonetheless, quietly balancing every journey you take through the fabric of existence. Different observers moving at different speeds will disagree about how much time passed or how far something traveled, yet there's a combined measure, a kind of space-time distance, that remains the same for everyone. It's like listening to the same gentle melody played by different instruments. The notes might shift in color, the tempo might stretch slightly, but the underlying tune remains recognizable and true. This space-time fabric has its own unique geometry, quite different from the familiar geometry of rulers and right angles. In everyday experience, the shortest path between 2 points is a straight line. But in space-time, the shortest path between 2 events is something called a world line, a continuous thread that shows where and when something exists, taking the route that requires the least effort through this 4-dimensional landscape. A resting object's world line points straight up through time, like a vertical pillar showing that it's moving only through time and not through space. A moving object's world line tilts slightly, blending space and time together in its trajectory. The faster something moves through space, the steeper that tilt becomes until for light itself. The world line lies at a perfect diagonal, representing the ultimate speed limit that nothing in the universe can surpass. To visualize how this geometry protects the order of cause and effect, physicists use something beautifully called a light cone. Imagine a bright flash occurring somewhere in space, a single spark like a distant lighthouse beam cutting through the darkness. Light spreads outward from that flash in every direction at the same unchanging speed, forming an ever-expanding sphere. If you draw that expansion through time, it creates a cone rising upward into the future and another descending into the past. Everything inside the upward cone represents events that the flash could possibly reach or influence later. Everything inside the downward cone represents events that could have influenced the flash before it happened. Outside both cones lies what physicists gently call elsewhere, events too distant in space or time to be connected, no matter how clever the messenger. This is nature's soft but firm way of enforcing order throughout the cosmos. Nothing can travel faster than light because nothing can move outside its cone. It's the universe's quiet rule for keeping time from contradicting itself, ensuring that cause always precedes effect. The light cone also reveals why past, present, and future are more than just convenient words. A galaxy shining 1 billion light-years away might be blazing with activity right now, but its present light won't reach Earth for another 1 billion years. In a very real sense, its now and your now are gently disconnected, separated by the fundamental architecture of space-time itself. The universe keeps each patch of reality honest to its own timeline, preventing paradoxes while maintaining the logical flow of existence. All of this might sound like abstract geometry, yet it describes something profoundly physical that touches your life in ways both subtle and profound. The clocks in satellites orbiting overhead tick at slightly different rates than those on Earth's surface, not because they're broken, but because their paths through space-time are different. Time itself flows at different rhythms depending on motion and gravity, like streams finding their own pace through varied terrain. This elegant unity of space and time would soon reveal how mass and energy don't just exist within this fabric, they actively shape it, bending the very geometry that guides everything from falling raindrops to orbiting planets along the gentlest possible paths through the cosmos. This elegant unity of space and time would soon reveal how mass and energy don't just exist within this fabric. They actively shape it, bending the very geometry that guides everything from falling raindrops to orbiting planets along the gentlest possible paths through the cosmos. But To understand how this cosmic guidance works, we must first reconsider something so fundamental that we rarely question it. What does it truly mean for something to move in a straight line? When you picture straightness, your mind probably conjures the edge of a ruler, the beam of a flashlight cutting through darkness, or the most direct route between 2 points on a map. These feel like absolute truths, unchanging definitions that would hold anywhere in the universe. But Einstein's profound insight revealed that straightness, like so much else we take for granted, is actually a relationship, a gentle conversation between motion and the geometry of the landscape through which that motion unfolds. Consider what happens. When you want to travel the shortest possible distance between two cities on Earth, your instinct might be to draw a straight line on a flat map, but that line, when traced on our curved planet, becomes a graceful arc. Airplanes follow these routes every day, sweeping over polar regions not because pilots enjoy scenic detours, but because these curves represent the most efficient paths across Earth's spherical surface. What appears bent on a flat chart is actually the straightest possible journey when you honor the true geometry of the world beneath your wings. In the four-dimensional fabric of space-time, these most efficient routes are called geodesics. They represent the paths that require the least effort, the most natural trajectories that objects follow when nothing pushes or pulls them away from their preferred motion. Every freely moving thing in the universe, from a planet orbiting its star to a beam of light crossing between galaxies, traces these invisible threads through the curved landscape of space and time. You can feel this principle by imagining a marble rolling across a smooth, stretched sheet. Give it a gentle push and it glides in a perfect line. Now place a heavy ball beneath the sheet, creating a shallow depression. The same gentle push sends the marble on a graceful curve, not because some invisible hand deflected it sideways, but because the sheet itself now offers a new definition of what straight means. The marble hasn't changed its intention. The surface has changed the meaning of simplicity. Replace that rubber sheet with space-time itself, and the marble with anything that moves, a planet, a photon, or even you walking across a room, and you have the essence of how gravity works in Einstein's universe. A planet circling the sun isn't being yanked inward by mysterious forces. It's not fighting against its natural tendency to drift away. Instead, it's doing exactly what comes most naturally, following the straightest possible path through the curved space-time that the sun's enormous mass has gently sculpted around itself. This is why the astronauts aboard the International Space Station float with such serene grace. They haven't escaped Earth's gravitational embrace, they're deep within it. They're simply gliding along Earth's geodesic, falling perfectly and perpetually as our planet's curvature guides their motion. If Earth weren't there, their path through space would indeed be a simple straight line stretching into infinity. But Earth's mass bends the fabric of reality into a subtle valley, turning that potential straight line into an endless, graceful loop. Inside the station, everything shares the same geodesic: the crew, the floating droplets of water, the gentle drift of untethered tools. Nothing presses against anything else because they're all following the same natural path through space-time's geometry. The sensation of weight only returns when something interferes with that motion, when a floor pushes up against feet or a wall provides resistance to natural drift. Even when you toss your keys in a gentle arc from hand to hand, what appears to your eyes as a simple parabola is actually a continuous, straight line through four-dimensional space-time. The keys never change their fundamental direction. They simply trace the path that Earth's curved geometry makes available, following the same natural law that guides distant galaxies and governs the motion of starlight itself. The profound democracy of geodesics becomes clear when you realize that everything follows them, regardless of mass, composition, or complexity. A grain of sand and a massive boulder released from the same height trace identical paths through space-time. When Apollo astronaut David Scott stood on the moon's airless surface and simultaneously dropped a hammer and a feather, they struck the lunar soil at exactly the same moment. They weren't obeying some special gravitational command. They were both following the same geodesic through the curved space-time around the moon. This universality reveals itself in the gentle behavior of light as well. When a beam of starlight passes near the sun, it bends ever so slightly, not because our star reaches out to grab something that has no mass to seize, but because the straightest available route through the sun's neighborhood is delicately curved. During that famous solar eclipse in 1919, when stars became visible near the sun's darkened edge, their light arrived shifted by just the whisper of an angle that Einstein had predicted, the sky's own signature confirming that even the swiftest travelers bow to geometry. You can detect this curvature by watching how nearby paths behave. Imagine two people starting side by side at Earth's equator, both walking due north along neighboring lines of longitude, neither ever turning left or right. In a flat world, they would remain the same distance apart forever. But on our curved planet, their paths gradually converge until they meet at the North Pole. This gentle drift of parallel geodesics toward or away from each other, what physicists call geodesic deviation, is how we recognize curvature even when we can't see it directly. The same principle plays out across the cosmos. Two asteroids drifting near Jupiter will have their trajectories subtly altered, not because the giant planet pulls on them with invisible strings, but because it shapes the very geometry of the space they move through. Their geodesics gently twist like threads in a cosmic fabric, bending around the presence of mass and energy. What makes this geometric view so profound is how it eliminates the need for mysterious forces reaching across empty space. When we say Earth orbits the Sun, we're not describing some invisible tether stretching across 50 million kilometers of void. We're describing the shape of space-time itself, the gentle curvature that the Sun's presence writes into the fabric of reality. Our star doesn't reach out to grab Earth, it simply exists. And that existence bends local geometry in such a way that Earth's most natural path happens to be a year-long loop. This transforms our understanding of motion throughout the universe. Every trajectory from the path of a single photon to the orbit of an entire galaxy becomes an expression of underlying geometry rather than the result of competing forces. The cosmos reveals itself as a vast landscape of invisible hills and valleys, with every object simply following the contours that mass and energy have carved into the structure of space-time itself. It's humbling to realize that every movement you make, every step, every gesture, every breath traces a thread in this vast geometric web. The shape of the cosmos quietly determines the story of all motion, and everything, without even trying, follows its graceful lines. You can picture each path as a gentle stream finding its way through an invisible landscape, always choosing the route that flows most naturally through the terrain. As we continue drifting through this curved universe, we'll discover that these same geodesics that guide motion through space also conduct something even more fundamental, the rhythm of time itself, flowing at different tempos depending on how deeply you rest within the valleys and hills of space-time's gentle topography. As we continue drifting through this curved universe, we'll discover that these same geodesics that guide motion through space also conduct something even more fundamental, the rhythm of time itself, flowing at different tempos depending on how deeply you rest within the valleys and hills of space-time's gentle topography. For time, it turns out, has no universal metronome beating steadily across the cosmos. Instead, it flows like a vast, invisible river with currents that quicken and slow, deepening into gentle eddies where gravity gathers, running swifter in the open spaces between worlds. This isn't a poetic metaphor, but measurable reality woven into the fundamental architecture of existence. The stronger gravity becomes, the more that temporal river deepens, and the more softly time itself begins to flow. Where mass pools densely around planets, near stars, in the hearts of galaxies, moments stretch longer than they do in the emptier regions beyond. Each massive object creates not just a depression in space, but a corresponding slowing in the passage of time itself, like a heavy stone dropped into the stream of seconds. You can witness this extraordinary truth without leaving your own quiet corner of the world. Imagine two identical atomic clocks, each capable of keeping time with almost unimaginable precision, synchronized to tick in perfect harmony like dancers moving to the same gentle music. Place one at sea level, deep within Earth's gravitational embrace, and carry the other to the summit of a tall mountain, where gravity's pull grows subtly weaker. As days unfold, something remarkable emerges from their measurements. The mountain clock gradually pulls ahead, gaining a few billionths of a second every 24 hours. The difference is absurdly small, invisible to your wristwatch, yet undeniably real and perfectly predictable. Time runs fractionally faster up there because the clock feels less of Earth's curvature tugging at the flow of moments. Down by the sea, where our planet's gravitational field is marginally stronger, time moves through its rhythm just a whisper more slowly. If your smartphone could speak, it might quietly boast about this cosmic fact, ticking ever so slightly ahead whenever you climb a hill or ascend in an elevator. This gravitational time dilation has been confirmed through increasingly elegant experiments. In the late 1950s, physicists Robert Pound and Glenn Rebka conducted a beautifully simple test using a tower at Harvard University. They sent gamma rays between the top and bottom floors, watching how the light's frequency shifted as it climbed through Earth's gravitational field. The rays became slightly bluer as they fell, their energy increasing by exactly the amount Einstein's equations predicted. Time at the bottom was indeed ticking slower than time at the top, and light itself carried that difference in its wavelength. Decades later, atomic clocks made these tests even more dramatic. Synchronized timepieces were flown in aircraft for hours, then compared with their earthbound twins. The airborne clocks had gained time by precisely the amount relativity predicted, confirming over and over that time is elastic, and gravity gently stretches its flow. The most practical demonstration of this cosmic truth lives quietly in your pocket. Every time you ask your phone for directions, you're relying on a constellation of satellites orbiting roughly 20,000 kilometers above Earth's surface. Each carries atomic clocks of extraordinary precision, and together they form the global positioning system that guides everything from delivery trucks to emergency rescues. But here's the remarkable thing. Without constant corrections for Einstein's time dilation, GPS would be completely useless for navigation. Those satellites experience gravity's effect on time in two distinct ways. First, they're racing around Earth at about 14,000 kilometers per hour, which causes their clocks to tick slightly slower due to their motion through spacetime. But simultaneously, they orbit far above Earth's surface where gravity is weaker, causing their clocks to tick faster than those on the ground. The two effects pull in opposite directions but don't cancel perfectly. The result is that satellite time gains about 38 microseconds every day compared to Earth time. That might sound insignificant, but when multiplied by the speed of light, it becomes enormous, about 11 kilometers of error per day. If engineers ignored Einstein's corrections, your GPS would think you were driving through buildings or floating in a nearby lake within hours. So before launch, satellite clocks are carefully set to tick slightly slower than those on Earth, perfectly offsetting the relativistic effects once they reach orbit. As they circle the planet, their time runs in harmony with ours, not because time itself is uniform, but because the differences have been precisely calculated and compensated. This means every time your phone shows your location, you're participating in an extraordinary technological achievement that functions only because we've learned to negotiate with curved space-time. Your phone quietly consults with satellites racing overhead, correcting for gravitational time dilation, orbital mechanics, and signal delay. Each location represents a small triumph of relativity in action, a conversation between everyday life and the geometry of the cosmos, whispered 1 microsecond at a time. Modern civilization, it turns out, runs on curved spacetime. Banks use GPS time to timestamp financial transactions. The Internet's backbone relies on synchronized clocks to manage data flow across continents. Scientific instruments depend on the same relativistic corrections to coordinate observations around the world. Einstein's equations didn't just redefine gravity, they became the quiet foundation of our connected world. There's something oddly comforting about discovering that time isn't brittle or unyielding. It listens, it adjusts, it has a gentleness to it, honoring location and motion with small courtesies. The universe doesn't keep a single time, but lets every corner breathe at its own pace. Time stretches softly around you every second of every day, a quiet reminder that even the most constant thing in the universe still knows how to bend. And time's gentleness reveals another face as well, one that shows itself not in the ticking of clocks, but in the color of light itself. For even photons, which cannot slow down or rest, must still climb out of the valleys carved by gravity, and when they do, they pay their own subtle price for the journey. And time's gentleness reveals another face as well, one that shows itself not in the ticking of clocks, but in the color of light itself. For even photons, those tireless travelers that cannot slow down or rest, must still climb out of the valleys carved by gravity, and when they do, they pay their own subtle price for the journey. Light is patient but not invincible. When it escapes from the gravitational embrace of a massive object, it loses a little energy with each step of its ascent, stretching its wavelength and shifting its color ever so gently toward the red end of the spectrum. This quiet transformation is called gravitational redshift, and it's one of the most elegant signatures of curved spacetime. Picture a single photon born near the surface of a star, perhaps emerging with the bright, energetic wavelength of blue or violet light. As it begins its journey outward, the star's gravity doesn't tug on it the way it would pull on a falling stone, for light has no mass to grasp. Instead, the photon must work against the curvature of spacetime itself, spending part of its energy just to escape the gravitational well that surrounds its birthplace. But here lies the beautiful constraint that governs all light. It cannot slow down. It always travels at the same cosmic speed limit, that fundamental constant woven into the fabric of reality itself. The only way for a photon to spend energy without changing speed is to change its tune. Its wavelength stretches, its frequency lowers, and its hue slides toward red. By the time it reaches the empty void beyond the star, it's still the same beam of light, just slightly older, slightly longer, carrying the gentle fatigue of its climb. This is different from the redshift caused by motion, where light stretches because its source is racing away like a receding train whistle dropping in pitch. It's also different from cosmological redshift, where the expansion of the universe itself pulls light longer as space grows between distant galaxies. Gravitational redshift is subtler and more intimate. Even if the source stands perfectly still, the geometry alone asks for its contribution. Light pays the fare not to distance or speed, but to depth, swimming upstream in that great river of time which runs a little slower near mass. You can witness this cosmic truth even here on Earth, though the effect is so delicate that only the most patient instruments can detect it. In the late 1950s, at that same Harvard University where precise clocks had confirmed time dilation, physicists Robert Pound and Glenn Rebka conducted one of the most elegant experiments in the history of physics. They sent gamma rays between the floors of a modest tower, watching how their frequency changed as they climbed through Earth's gravitational field. When the light fell downward, it gained energy, becoming ever so slightly bluer. When it traveled upward, it lost energy, becoming redder. The difference was less than 1 part in 100 trillion, yet the universe played along faithfully, confirming Einstein's predictions with extraordinary precision. Time ran a whisper slower at the bottom than at the top, and the photons carried that truth in their color, like messengers bearing news of spacetime's gentle slopes. Near more massive objects, this toll grows dramatically. Light, leaving the surface of a white dwarf, the dense ember of a collapsed star, emerges noticeably redder than when it began its journey. From a neutron star where matter is squeezed into a city-sized sphere containing more mass than our entire sun, the effect becomes staggering. A photon escaping such a surface feels the steepness of spacetime's slope so keenly that it arrives at distant telescopes having paid a conspicuous share of its original energy. Astronomers use this cosmic taxation system to weigh stars at impossible distances, reading their gravity from the tint of their light without ever touching them. You can visualize gravitational redshift as light behaving like a determined climber, ascending an invisible hill of gravity. At the base, near a massive object, the climber steps with vibrant energy, each movement packed with momentum. As it ascends, each step costs effort. There's no friction, no wind, no resistance except the invisible slope of space-time itself. By the time it reaches the summit far from the gravitational source, its steps are longer, its rhythm slower. It hasn't lost heart, but it has lost energy, stretched thin by the long climb out of gravity's embrace. This principle works in reverse too, creating gravitational blue shift. When light falls toward a massive body, it doesn't slow down, but its frequency increases as it gains energy from the descent. The color shifts toward blue, showing that gravity doesn't just stretch light, it can compress it too, depending on the direction of travel. The universe keeps careful accounts. Photons don't cheat the rules. The same sensitivity that forces GPS satellites to respect time dilation also compels our instruments to account for gravitational redshift. Light from the center of massive galaxies where supermassive black holes anchor the cosmic architecture arrives slightly stretched compared to light from the outer regions. By measuring these subtle differences, astronomers can map the invisible distribution of matter, including the dark matter that shapes but doesn't shine. Even our own sun displays this effect. Light from its surface shows a measurable redshift compared to the same elements glowing in Earth-based laboratories. The difference is small but consistent, providing yet another confirmation that space-time curves around every massive object, creating invisible valleys from which even light must work to escape. The beauty of gravitational redshift lies in how it connects the grandest and most intimate scales of physics. Every photon that leaves a planet, a star, or a galaxy carries with it a record of the gravitational journey it has made. Most of the time the toll is tiny, barely perceptible. But in the deep wells carved by the universe's most massive objects, the cost becomes enormous, and light itself grows genuinely weary on its climb to freedom. So the next time you see the soft glow of starlight, remember that those gentle rays have paid their toll in energy to reach your eyes. They've climbed out of gravitational wells both deep and shallow, stretched just a fraction by their journey through the curved fabric of space and time. It's a delicate reminder that even light, for all its speed and brilliance, still honors the geometry of the universe, sometimes catching its breath on the long way out of a star's embrace. And yet, light's interaction with curved space-time reveals even more profound truths. For if gravity can stretch the color of light, perhaps it can also bend its very path, creating invisible lenses that allow the universe to photograph itself through the gentle artistry of geometric deflection. Light, for all its speed and brilliance, seems like it should be immune to gravity's influence. After all, photons have no mass, nothing for gravity to grasp, no substance to pull upon. Yet the universe has a quiet way of humbling even its swiftest traveler. When light passes near something massive like our sun, its path curves ever so slightly, not because the light is being tugged or slowed, but because the space it moves through is itself gently curved. The photon continues doing exactly what it always does, following the straightest possible route through whatever geometry spacetime offers. It's just that in curved spacetime, straight doesn't always look straight to distant observers like us. Picture a beam of starlight as a silk ribbon stretched across the cosmos, moving with unwavering determination along what it perceives to be a perfectly straight line. When spacetime curves near a massive object, that ribbon naturally follows the bend, like a delicate scarf drifting gracefully over the contours of an invisible sphere. The light doesn't fall into the curve or struggle against it. It simply glides across the topology of reality, smooth and unhurried, obeying the geometry that mass and energy have written into the fabric of existence. Einstein predicted this subtle deflection in 1915 when he first completed his general theory of relativity. His calculations suggested that light passing near the sun's edge should bend by about 1 3/4 arc seconds, a vanishingly small angle roughly equivalent to seeing a coin shift by the width of a hair from several kilometers away. It was a bold prediction that could only be tested during those rare moments when the sun's overwhelming glare was blocked by the moon during a total solar eclipse. That extraordinary opportunity arrived in May of 1919, just 4 years after Einstein's prediction. 2 British expeditions set out under the leadership of astronomer Arthur Eddington, one sailing to the island of Principe off the west coast of Africa, another traveling to Sobral in Brazil. Their mission was elegantly simple, yet technically demanding: to photograph the stars visible near the sun's darkened disk during totality and compare their apparent positions with where those same stars appeared in the night sky when the sun was elsewhere as the moon slid across the sun that May morning. The day darkened into an ethereal twilight, and stars near the eclipse came into view with crystalline clarity. Using long-exposure photographic plates, Eddington and his colleagues captured these stellar positions with patient precision. When the plates were later developed and analyzed, they revealed exactly what Einstein had predicted. The starlight nearest the sun appeared slightly displaced, shifted outward by precisely the tiny angle his equations had foretold. It was a quiet revolution, recorded in silver emulsion on glass. Newspapers proclaimed lights all askew in the heavens, and Einstein became a household name overnight. But beneath the headlines lay a gentler truth. The test had confirmed that space itself could bend, and that light, obedient and tireless, would trace those bends with perfect fidelity. Once astronomers knew how to look, they discovered this bending wasn't confined to our solar neighborhood. It happens everywhere throughout the cosmos, on every scale where mass gathers. When light from distant galaxies passes through the curved spacetime created by massive clusters in the foreground, the images we see can be stretched, magnified, or even multiplied. Sometimes the alignment is so precise that the light forms a complete ring around the lensing mass, what astronomers now call an Einstein ring. Other times we see graceful arcs and elongated smears, the cosmic fingerprints of invisible curvature guiding ancient light on gentle detours toward our telescopes. This gravitational lensing has become one of astronomy's most powerful tools, allowing us to map what we cannot otherwise see. Dark matter, which refuses to shine, still bends light with perfect honesty. By measuring the subtle distortions of thousands of background galaxies, we can reconstruct the hidden scaffolding of the cosmos. The universe, in effect, provides its own telescope, using the curved space-time around massive objects to focus and magnify light from even more distant sources. What makes this deflection so profound is how it works. Gravity doesn't reach out to grab the light as it passes. The photon isn't changing its fundamental behavior or responding to some mysterious tug. It's simply doing what light always does, traveling in the straightest possible line through whatever space-time offers it. If space-time bends, the path bends too, as naturally as water following the contours of a stream bed. The amount of bending reveals the mass doing the lensing. Near our Sun, the effect is tiny but measurable. Near the supermassive black holes that anchor galactic centers, the deflection can be dramatic. Light can even orbit such objects several times before escaping, tracing loops in the intense curvature like a dancer spinning at the edge of an invisible stage. Every beam of starlight reaching your eyes tonight has been gently deflected by planets, stars, and galaxy clusters along its path, each leaving a subtle signature in the light's trajectory. You're seeing not just the distant source, but the entire landscape of gravity between here and there, written in the gentle curves that guided the photons on their billion-year journey. The beauty of Einstein's prediction and its confirmation lies in how it revealed light to be intimately connected to the gravitational architecture of the universe. Light showed itself to follow the contours carved by mass and energy, while gravity revealed itself to be not a mysterious force reaching across emptiness, but the shape of reality itself. And just as individual beams of starlight reveal the curvature around distant objects, so too do the motions of entire worlds reveal the contours closer to home. Each planet and moon traces not a forced circle through space, but the straightest possible curve through a landscape that invites an endless, graceful fall. And, just as individual beams of starlight reveal the curvature around distant objects, so too do the motions of entire worlds reveal the contours closer to home. Each planet and moon traces not a forced circle through space, but the straightest possible curve through a landscape that invites an endless, graceful fall. In the quiet rhythm of the cosmos, every celestial body is falling. Earth is falling around the Sun, the Moon is falling around Earth, and even our Sun itself is falling slowly around the center of our galaxy in a stately dance that takes 250 million years to complete. Yet none of these worlds crash into one another. They fall perfectly, perpetually, tracing elegant loops through the fabric of space-time like dancers who have found their rhythm and never need to stop. When Newton first gazed at the planets gliding across the night sky, he saw a grand cosmic balance of competing forces. The Sun's gravity, he reasoned, tugged each planet inward, while the planet's forward motion tried to carry it away in a straight line. The result was a stable orbit, an endless compromise between falling and flying that kept the solar system in harmonious order. For centuries, this picture explained the heavens with mathematical beauty, allowing astronomers to predict eclipses and chart the wandering paths of comets with extraordinary precision. But Einstein's vision transformed that cosmic tug-of-war into something far more serene. In his curved universe, the planets aren't being pulled at all. They're free-falling along the straightest possible paths through the geometry that the Sun's enormous mass has written into space-time. It's an elegant shift in perspective. From our vantage point, we see circular and elliptical orbits as though the planets were whirling in invisible harnesses. In reality, they're doing nothing more than following the natural contours of curved space-time, as effortless as leaves drifting along a gentle stream. If space-time around the Sun were perfectly flat, the planets would indeed drift in straight lines forever, never to return. But because the Sun's mass bends that four-dimensional geometry, creating a vast invisible well in the fabric of reality, the straightest possible path becomes a graceful arc that loops back on itself. The result is an orbit, a continuous fall that never quite reaches the bottom, like throwing a ball hard enough that it keeps missing the ground because Earth's surface curves away beneath it at just the right rate. Consider the International Space Station, racing around Earth at about 28,000 kilometers per hour. From our perspective on the ground, it appears to be constantly falling toward our planet, while somehow never hitting the surface. But from the astronaut's quiet perspective inside, they're simply drifting in perfect tranquility. They're not fighting against gravity or being held up by anything at all. They're following the most natural path available through Earth's curved geometry, falling freely and perpetually as our planet's surface curves away beneath them at precisely the right rate. Inside the station, everything shares the same geodesic: the crew, the floating droplets of water, the gentle drift of tools and equipment. Nothing presses against anything else because they're all following the same natural path through spacetime's geometry. The sensation of weight only returns when something interrupts that motion, when a wall provides resistance, or when engines fire to change course. What we call weightlessness isn't the absence of gravity, it's the presence of perfect freedom to follow gravity's geometric guidance. Each orbit represents a delicate balance between motion and curvature. Move too slowly through space-time, and the path spirals inward toward the central mass. Too fast, and it escapes the gravitational valley entirely, sailing off into the darkness between worlds. Somewhere in between lies the sweet spot, where objects keep falling but never reach the bottom, forever tracing the elegant curves that mass and energy have carved into the structure of reality. One of the most beautiful confirmations of this geometric view emerged from studying Mercury, the innermost planet racing closest to the Sun's intense gravitational field. For decades before Einstein, astronomers had puzzled over a curious feature of Mercury's orbit. Each time the planet completed its elliptical journey around the Sun, the ellipse itself had rotated slightly, causing Mercury's point of closest approach to creep forward by a tiny but persistent amount, 43 arc-seconds per century. Most of this orbital precession could be explained by gravitational influences from other planets. But even after accounting for every known effect, that small remainder persisted like a cosmic whisper hinting at deeper truths. Einstein's equations solved the mystery perfectly. The extra precession wasn't due to any hidden force or invisible planet. It was simply Mercury faithfully following its geodesic through the Sun's curved space-time, where the geometry itself twisted ever so slightly with each orbit. Mercury's path recorded that twist with exquisite precision, like a sensitive stylus tracing the subtle undulations of the cosmic fabric. The profound beauty of orbital motion in Einstein's universe lies in its democracy. Every object, regardless of mass or composition, follows the same geometric rules. A grain of dust and a massive planet placed in the same location with identical velocity would trace identical paths through space-time. They're not obeying commands from gravity. They're reading the same invisible map, written by the distribution of mass and energy around them. Even the shapes of orbits emerge naturally from this geometric perspective. Circular orbits occur when objects move at just the right speed to follow closed geodesics. Elliptical orbits happen when the motion is slightly different, creating paths that stretch and compress but still return to themselves. The sweeping parabolas and hyperbolas of visiting comets represent geodesics that pass through the inner solar system once before heading back toward infinity, following the straightest possible routes through a geometry that allows them to visit and continue onward. From the smallest asteroid to the grandest galaxy, the same quiet principle governs all motion. Objects don't need instructions. The steps are inscribed on the floor of space-time itself. The inner planets race swiftly around the Sun because they sit deeper in the gravitational valley where faster motion is required for stability. The outer giants drift leisurely for decades because they inhabit the gentler slopes where slower tempos suffice. Each world keeps time to the rhythm that the geometry beneath it provides. You can picture the solar system not as objects held in place by competing forces, but as a collection of threads weaving through the same cosmic tapestry. Each planet traces its own ribbon around the Sun's curved geometry, bound not by chains but by the simple perfection of following the straightest available path. Together, these threads form the harmony we observe, each orbit maintaining its own tempo while participating in the same geometric symphony. The next time you look up at the moon, remember that it's not hanging in space or being held aloft by some mysterious force. It's falling gracefully and endlessly along the curve of space-time that Earth's presence has gently sculpted. What keeps it in its celestial dance isn't resistance to gravity, but perfect obedience to it, following the natural lines that mass and energy have drawn across the fabric of reality. And when we turn our attention beyond the solar system, we discover that this same principle of geometric guidance creates even more extraordinary phenomena. The universe itself becomes a vast natural observatory, where the curvature of space-time around massive objects transforms distant galaxies into cosmic telescopes, focusing and magnifying light from the farthest reaches of space and time. And when we turn our attention beyond the solar system, we discover that this same principle of geometric guidance creates even more extraordinary phenomena. The universe itself becomes a vast natural observatory, where the curvature of space-time around massive objects transforms the cosmos into its own photographer, focusing and magnifying light from the farthest reaches of space and time. Light, on its billion-year journey across the universe, almost never takes a perfectly straight path. It threads between galaxies, slips past massive clusters, and grazes concentrations of matter, both seen and unseen. Each encounter leaves a gentle trace on its trajectory, a subtle curve written into the light's path by the same geometric principles that guide planets in their orbits. Sometimes, when the cosmic alignment is just right, these gentle deflections turn space-time into a natural lens, crafted not by glass or mirrors, but by the invisible architecture of curved geometry itself. This phenomenon, called gravitational lensing, happens whenever light from a distant source passes near something massive on its way to our telescopes. The gravity of the foreground object, whether it's a single galaxy, a cluster of thousands of galaxies, or even something completely invisible, bends the path of the background light, changing how that distant source appears to us. The universe, in effect, takes its own portrait using nothing but the curved space-time around massive objects as its camera. The effects can be breathtakingly beautiful. When the alignment is nearly perfect and the foreground mass enormous, we witness what Einstein himself predicted but doubted anyone would ever observe: complete rings of light encircling the lensing object. These Einstein rings appear as perfect circles of brilliant illumination, created when a distant galaxy's light is bent equally in all directions around a massive foreground cluster. They're so symmetrical they look almost artificial, yet they're crafted by nothing more than the gentle curvature of space-time, like cosmic halos drawn by geometry alone. More commonly, we see graceful arcs and elongated smears of light, the distorted images of galaxies whose ancient radiance has been stretched and magnified by the gravitational landscape it encountered along its journey. One of the most stunning examples captured by the Hubble Space Telescope shows the galaxy cluster Able 1689, a vast collection of hundreds of galaxies bound together by gravity. Behind it lies an even more distant field of galaxies whose light has been curved into delicate blue arcs that wrap around the cluster's core like streamers caught in an invisible whirl. These aren't artistic interpretations. They're the literal bending of starlight that left its source when the universe was young, only to be gracefully redirected on its final approach to our instruments. Sometimes the cosmic choreography becomes even more remarkable. The lensing cluster, MAX J149.5L2-223, produced multiple images of a distant supernova nicknamed Refstal. The light from that single exploding star was bent along several different paths by the cluster's gravity, arriving at Earth at different times like echoes of the same cosmic event. Astronomers witnessed the same supernova flare appear, fade, and then reappear months later in another part of the sky, as if the universe had recorded the explosion for us and was playing it back in slow motion across space-time. But gravitational lensing reveals something even more profound than these beautiful distortions. It allows us to map the invisible scaffolding of the cosmos. When astronomers study these lensed images carefully, they discover that the amount of bending is far greater than can be explained by the visible matter alone. All the bright stars and glowing gas that we can observe directly. The curvature of space-time around massive clusters is shaped by something that doesn't emit or absorb light, something that interacts through gravity alone. This hidden substance, which we call dark matter, makes up roughly 5 times more mass than all the ordinary matter in the universe combined. Through weak gravitational lensing, where thousands of background galaxies are each stretched by tiny, almost imperceptible amounts, astronomers can reconstruct detailed maps of this invisible architecture. They find vast halos of dark matter surrounding every galaxy, invisible threads connecting clusters across millions of light-years, and intricate web-like structures that guide the formation of everything we see in the night sky. Dark matter reveals itself not by shining but by the way it bends starlight, like reading the shape of an invisible hand by watching how it curves the light that passes through its fingers. Even on the most intimate scales, this cosmic lensing continues its quiet work. When a single star passes directly in front of a more distant one, the foreground star's gravity can focus the background star's light, causing it to brighten temporarily in a characteristic way. This microlensing effect has become a powerful tool for discovering planets orbiting distant stars, revealing entire worlds through nothing more than a momentary brightening of ancient starlight. A tiny flicker can betray the presence of a Jupiter-sized world thousands of light-years away, detected not by its own light, but by how it briefly magnifies the light of something even more distant. There's something profoundly beautiful about this cosmic photography. Every beam of starlight that reaches our telescopes carries with it a complete record of the gravitational landscape it has traversed. The photons don't just tell us about their distant sources, they map the entire terrain of matter and energy that guided their journey. We're seeing not just what shines, but what shapes the seeing itself. Each arc and ring becomes a measurement in disguise, revealing how much mass lies hidden in the cosmic lens and how it's distributed across space. The universe, patient and generous, provides its own instruments for exploring the depths of space and time. Every massive object becomes a potential telescope, every curved region of space-time a possible magnifying glass. The same geometric principles that guide apples falling from trees and moons orbiting planets operate on the grandest scales, turning the entire cosmos into a vast optical system that focuses, magnifies, and reveals the hidden architecture of reality. As light traces these gentle curves across billions of years and billions of light-years, it reminds us once again of the democratic nature of Einstein's universe. Whether it's a photon bending around the sun or ancient galactic light curved by invisible dark matter, everything follows the same geometric rules written into the fabric of space-time. The cosmos reveals itself as a place where nothing travels alone, where every journey is guided by the invisible hand of curved geometry. And sometimes, when the most massive objects in the universe undergo the most dramatic transformations, when black holes spiral together or neutron stars collide in the deep reaches of space, that gentle fabric of space-time doesn't just bend light along new paths. It ripples and rings, sending waves of pure geometry racing outward across the cosmos, carrying news of events so powerful they can make the entire universe tremble with their gravitational song. And sometimes, when the most massive objects in the universe undergo the most dramatic transformations, when black holes spiral together or neutron stars collide in the deep reaches of space, that gentle fabric of space-time doesn't just bend light along new paths. It ripples and rings, sending waves of pure geometry racing outward across the cosmos, carrying news of events so powerful they can make the entire universe tremble with their gravitational song. If you could somehow hold the cosmos in your hands and shake it, you'd feel it hum. Not metaphorically, but literally. Space-time itself is elastic, and when something truly massive accelerates through its depths, the very fabric of reality vibrates like the surface of a vast, invisible drum. Einstein predicted these gravitational waves in 1916, just a year after completing his general theory of relativity. If gravity truly was the curvature of space-time, he reasoned, then accelerating masses should create disturbances in that curvature, much like a stone dropped into a still pond sends ripples across the water's surface. But these would be ripples in space-time itself, racing outward at the speed of light, stretching and squeezing space as they passed through everything in their path, including you, right now, as you listen to these words. For nearly a century, these waves remained purely theoretical, thought to be far too faint to ever detect directly. They stretch and compress space by less than the width of a proton over distances of kilometers, changes so minuscule that even the most energetic cosmic collisions would barely nudge space-time here on Earth. Einstein himself doubted we'd ever develop instruments sensitive enough to measure them. The challenge seemed impossible. Detecting a change smaller than 1,000th the width of a proton across a distance of several kilometers, roughly equivalent to noticing a hair's thickness compared to the distance from Earth to the nearest star. But physicists, as it turned out, are extraordinarily patient when faced with the impossible. By the late 20th century, technology had finally caught up to imagination. Scientists built the most sensitive measuring devices ever conceived, the twin LIGO detectors, standing like monuments to human curiosity in Louisiana and Washington. Each facility is shaped like a giant letter L, with 2 tunnels stretching 4 kilometers in each direction. Inside those arms, lasers bounce back and forth between mirrors thousands of times, creating a listening so delicate that the hum of Earth itself must be quieted. Seismic tremors, distant traffic, even the whisper of air, all tamed until only space-time's murmur remains. The principle is elegant in its simplicity. When a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction, like the gentle breathing of the cosmos itself. One arm of the detector grows infinitesimally longer, while the other shrinks by the same tiny amount. The laser light traveling back and forth through this subtly changing geometry creates an interference pattern that reveals the wave's passage with extraordinary sensitivity. Then, on September 14, 2015, at 5:51 in the morning Eastern Time, something extraordinary happened. Both LIGO detectors, separated by thousands of kilometers, simultaneously recorded a faint signal lasting just 0.2 of a second. It was a quick, rising chirp, a frequency that started low and swept rapidly upward before cutting off sharply. When scientists converted that gravitational wave signal into sound, what they heard was surprisingly musical, a low rumble that climbed quickly in pitch, like the final heartbeat of something immense and ancient before falling silent forever. What they had captured was the death song of 2 black holes, each about 30 times more massive than our Sun, that had been spiraling around each other for eons in a galaxy over 1 billion light-years away. As they drew closer and closer, orbiting faster and faster, they stirred space-time into increasingly violent ripples until, in that final fraction of a second, they merged into a single, larger black hole. The collision released more energy and gravitational waves than all the stars in the observable universe emit in light, a burst of pure geometry so powerful it shook the fabric of reality across cosmic distances. The discovery was announced in February 2016, almost exactly 100 years after Einstein's prediction, transforming gravitational wave astronomy from dream to reality. For the first time in human history, we weren't just looking at the universe, we were listening to it. The cosmos, it turned out, had been broadcasting a symphony all along, but only now did we have ears sensitive enough to hear its music. What makes gravitational waves so powerful as messengers is their shyness. They barely interact with matter at all, passing through stars, galaxies, and our own bodies with almost no distortion. Unlike light, which can be absorbed or scattered by dust and gas, gravitational waves pass through everything unhindered, carrying pristine information straight from their source. They arrive essentially unchanged, bearing news from the invisible depths of space where matter and energy dance their most extreme choreographies. Since that first detection, LIGO and its partner observatories, Virgo in Italy, Kagra in Japan, have recorded dozens of these cosmic collisions. Each one has its own signature, its own unique timbre that reveals the masses and spins of the objects involved. From less than a second of space-time distortion, scientists can reconstruct the final moments of objects so massive and dense that they challenge our understanding of matter itself. Perhaps the most remarkable detection came in August 2017, when gravitational waves and light were observed from the same cosmic event for the first time. Two neutron stars, incredibly dense remnants of collapsed suns, spiraled together and merged in a galaxy 130 million light-years away. The gravitational waves arrived first, followed by gamma rays, then optical light, then radio waves. For the first time, humanity witnessed a single cosmic event through multiple messengers, hearing the space-time ripples while simultaneously watching the explosion's brilliant aftermath forge gold and platinum in the cosmic fire. There's something profoundly moving about the fact that these ripples are always there, flowing through us unnoticed. Right now, countless gravitational waves from countless cosmic events are passing through your body, through Earth, through the solar system, each one a faint echo of some distant drama played out in the depths of space and time. The universe sings constantly in frequencies we've only just learned to hear, and every note carries news of the ongoing dance between matter, energy, and the curved space-time that holds them all. As we develop even more sensitive instruments and launch gravitational wave observatories into space, we'll hear deeper into the cosmic symphony, perhaps even catching echoes from the universe's first moments. But the most common authors of these songs, the ones that lean hardest on the strings of space-time, are not monsters at all, but masterpieces of geometry, regions where the curves become so deep that all paths point inward, where even light cannot find a way out. But the most common authors of these songs, the ones that lean hardest on the strings of space-time, are not monsters at all, but masterpieces of geometry, regions where the curves become so deep that all paths point inward, where even light cannot find a way out. At first glance, the idea of a black hole sounds like something from a cosmic nightmare, a place where gravity grows so intense that not even the swiftest beam of light can escape its grasp. Yet behind that dramatic reputation lies one of the most elegant creations in nature's repertoire, a simple and precise consequence of the very geometry we've been exploring together. A black hole isn't a ravenous monster devouring everything in its path, nor is it a bottomless pit through which the universe drains away. Instead, it's the inevitable outcome when enough mass is packed into a small enough volume, causing space-time to curve in on itself so completely that it creates a region where all possible paths, no matter how determined, eventually point inward. What we call a black hole is really just the most profound shape that space-time can take, a deep, silent well in the cosmic fabric sculpted by nothing more than the patient mathematics of curved geometry. The architecture of these cosmic sculptures is surprisingly straightforward. defined by two key features that dictate their mysterious behavior. At the outer boundary lies the event horizon, what physicists gently call the edge of silence. There's nothing to touch there, no surface, no membrane, no wall you might crash into. Instead, it's simply a boundary woven entirely from space-time itself, the precise point where the escape velocity equals the speed of light. Anything crossing that invisible threshold, whether it's a photon racing at cosmic speed or a spacecraft under full power, becomes forever cut off from the outside world, not because it's immediately destroyed, but because all possible paths from that point onward lead inexorably deeper into the geometric well. Deep still, at the very center, lies what our equations call the singularity, a point where density appears to become infinite and our current laws of physics break down completely. In reality, physicists suspect this isn't truly a point at all, but rather a region where the known laws of the universe simply stop applying, awaiting a deeper theory of quantum gravity to explain what happens there. For now, the singularity remains hidden behind the event horizon, unobservable and unreachable, its true nature cloaked in geometric mystery. From a safe distance, black holes behave in surprisingly predictable and gentle ways. They're remarkably simple objects, described completely by just their mass and their spin. That's all you need to predict how they'll bend light, distort time, and influence the surrounding cosmos. Despite their reputation for chaos, black holes are astonishingly elegant in their mathematical simplicity, like perfectly sculpted spheres of pure gravitational geometry. One of the most striking effects they produce is gravitational time dilation, amplified to extraordinary extremes. To an outside observer watching from a comfortable distance, a clock falling toward a black hole would appear to tick slower and slower as it approaches the event horizon. Light from the falling object would grow redder and fainter, eventually seeming to freeze just above the edge, never quite disappearing, but fading into an eternal, red-shifted twilight. From the outside universe's perspective, nothing ever truly falls into a black hole. Everything just hovers eternally at the threshold, stretched beyond sight. But from the viewpoint of the falling object itself, the experience is entirely different and surprisingly calm. Time flows normally, and the horizon is crossed in a finite, unremarkable moment. The traveler passes smoothly through what appeared from outside to be an impenetrable barrier, unaware that the rest of the universe has seemingly rushed forward in time. It's one of relativity's most profound demonstrations of how perspective shapes reality. Both experiences are equally valid, equally true, depending on which reference frame you call home. Another common misconception paints black holes as cosmic vacuum cleaners, greedily sucking in everything nearby. The geometric truth tells a softer story. Replace our sun with a black hole of precisely the same mass, and Earth's orbit would continue almost unchanged. Daylight would vanish and tides would shift, but our path through space would remain the same. Outside the event horizon, gravity still follows the familiar inverse square law. There's no mysterious suction, just the same geometric principles we've been exploring, drawn more tightly near the center. The real drama near black holes comes from tidal forces, the same principle that lifts Earth's oceans toward the moon, but amplified to extraordinary extremes. Because gravity changes rapidly with distance near a black hole's horizon, different parts of an approaching object feel dramatically different gravitational pulls. Near smaller black holes, where the curvature is incredibly steep, this difference can be catastrophic. A person falling feet first would be stretched vertically and compressed horizontally in a process whimsically nicknamed spaghettification. But scale matters enormously. For the supermassive black holes found at galactic centers, millions or billions of times more massive than our Sun, the tidal gradient near the event horizon is surprisingly gentle. You could cross it without feeling anything unusual at all, only encountering the fiercer curves much deeper within. Black holes are also among the universe's most efficient engines for converting matter into energy. As material spirals inward, it doesn't fall directly into the abyss, but forms a hot, luminous accretion disk, like a cosmic whirlpool of gas and dust. Friction and magnetic fields heat this disk to millions of degrees, causing it to blaze across the electromagnetic spectrum and outshine entire galaxies. The black hole itself remains utterly silent and dark. It's the surrounding chaos of transformation that creates such brilliant displays, a cosmic halo of creative destruction where matter dances its final luminous dance before crossing the point of no return. In one of physics' most beautiful ironies, black holes aren't completely black. In the 1970s, Stephen Hawking discovered that quantum effects near the event horizon allow black holes to emit a faint glow. Virtual particle pairs that normally appear and disappear in the vacuum can be separated by the intense curvature, with one particle escaping while the other falls in. To distant observers, this appears as gentle radiation, showing that even the most extreme geometries in the universe still honor the subtle laws of quantum mechanics. For stellar and supermassive black holes, this Hawking radiation is far too faint to observe today, but it tells us that the horizon whispers in quantum frequencies, slowly returning its borrowed energy to the cosmos over unimaginable stretches of time. For decades, black holes existed only in equations and theoretical discussions, glimpsed indirectly through their effects on nearby matter and light. Then, in 2019, the Event Horizon Telescope, a network of radio dishes spanning the globe, gave us something approaching direct sight. By linking telescopes across continents, astronomers created a virtual Earth-sized observatory capable of resolving the tiny region around the supermassive black hole in the galaxy M87. The resulting image was extraordinary. A dark, circular shadow surrounded by a glowing, asymmetric ring of hot gas. The shadow wasn't the black hole itself, but rather the silhouette cast by its gravity, the region where light is bent so severely that it orbits several times before escaping or falling in. For the first time, humanity had seen the outline of curved spacetime at its most extreme, a photograph of shaped geometry itself. What emerges from this deeper understanding is a picture of black holes not as cosmic villains, but as the universe's most accomplished architects. They anchor the centers of galaxies, regulate the birth of stars, and drive some of the most spectacular phenomena we observe across the cosmos. Without the supermassive black hole quietly resting at the center of our own Milky Way, the graceful spiral of hundreds of billions of stars might never have formed. They represent not destruction, but creation by another name, regions where matter, energy, and spacetime itself are recycled and transformed according to the deepest laws of physics. There's a quiet poetry in recognizing that these objects, which seem to embody ultimate darkness, are actually expressions of pure geometric beauty. They remind us that even the most extreme phenomena in the universe follow the same gentle principles we've been exploring. Matter shapes spacetime, spacetime guides motion, and everything unfolds according to the elegant mathematics of curved reality. The same geometry that makes time slow to a standstill also drives the engines of cosmic evolution, recycling matter and stirring galaxies with invisible brushstrokes of curvature. And as these massive objects spin through the cosmos, they reveal yet another layer of spacetime's responsiveness. They don't just bend the fabric of reality, they drag it along with them, creating swirling currents in the very foundation of existence itself. Like cosmic whirlpools where even the notion of standing still begins to lose its meaning. And as these massive objects spin through the cosmos, they reveal yet another layer of spacetime's responsiveness. They don't just bend the fabric of reality, they drag it along with them, creating swirling currents in the very foundation of existence itself. Like cosmic whirlpools where even the notion of standing still begins to lose its meaning. When Einstein first described gravity as the curvature of spacetime, He gave us a universe where mass shapes geometry. But hidden within those elegant equations was another profound subtlety: rotation. When something massive spins, it doesn't merely bend space-time, it drags the fabric along with it, stirring the cosmic medium like honey being slowly churned by an invisible spoon. This phenomenon, called frame dragging, is one of the strangest, most beautiful consequences of general relativity. Imagine space-time not as an empty void, but as a thick, responsive medium that can be twisted and stirred. When a heavy object like a spinning planet or star rotates within it, the nearby layers of space-time are gently pulled along, as if the rotation was stirring cosmic honey. The faster the spin and the denser the object, the stronger this twisting becomes. Close enough to a rotating black hole, this effect becomes so intense that space-time itself begins to swirl at nearly the speed of light. Frame dragging is profoundly different from any force we experience in daily life. It's not gravity pulling on objects, it's space itself rotating. If you could stand near a spinning planet with a perfect gyroscope in your hands, you wouldn't feel any sideways push. Instead, the local geometry would quietly carry you along with it. The gyroscope's axis would drift ever so slowly, as if a gentle current were tugging at the very notion of straight itself. Orbits would shift by whispers. Time would take a slightly different path than expected. You wouldn't feel the twist directly, but the most sensitive instruments would detect it, revealing the invisible currents flowing through the fabric of reality. For nearly a century after Einstein predicted this effect, it remained purely theoretical, too subtle to measure with earthbound instruments. But in 2004, one of the most delicate experiments ever conceived finally confirmed that space-time really does twist around spinning objects. NASA's Gravity Probe B mission was a masterpiece of precision engineering, designed to test whether Earth's gentle daily rotation actually drags the geometry of space around with it. The concept was elegantly simple. Place 4 perfectly spherical gyroscopes in orbit around Earth and measure whether their axes of rotation gradually drifted over time. If space-time were perfectly still, those axes would remain fixed forever, always pointing toward the same distant guide stars like cosmic compass needles that never wavered. But if Earth's rotation dragged space-time around with it, the gyroscope orientations would slowly drift in a characteristic pattern, revealing the invisible swirl of the cosmic medium. The precision required was almost beyond imagination. Each gyroscope was crafted from fused quartz and polished so perfectly that it deviated from a perfect sphere by less than 40 atomic layers, the smoothest objects ever created by human hands. They were suspended in vacuum and cooled to near absolute zero to minimize vibrations, shielded from magnetic interference, and monitored with laser beams sensitive to motions smaller than the width of a proton. Every tremor, every signal from the spacecraft had to be measured and accounted for with extraordinary care. For over a year, the satellite orbited Earth in peaceful silence, quietly measuring the geometry of space around our spinning planet. As the data accumulated, the results matched Einstein's predictions with remarkable precision. The gyroscope axis had indeed shifted by about 37 thousandths of a degree per year, exactly the amount expected if Earth were dragging the fabric of space-time around with it. The confirmation came almost exactly 100 years after the effect was first predicted, transforming frame dragging from elegant theory into measured fact. Around more compact, rapidly spinning objects, frame dragging becomes a dominant feature of reality. Near a rotating black hole, the effect is so powerful that space-time itself whirls around at nearly the speed of light. In this region, called the ergosphere, nothing can remain stationary. Even light is forced to move in the direction of the spin, caught in the cosmic current like leaves swept along by a rushing river. Any object entering this zone must rotate with the black hole. It's like being caught in a whirlpool, where the water itself is the riverbed. this twisting of space-time, helps explain some of the universe's most spectacular phenomena. Many black holes and neutron stars are surrounded by disks of hot gas that spiral inward while launching powerful jets of material along their spin axes. These jets can extend for thousands of light years, shooting streams of plasma at nearly the speed of light across intergalactic distances. Frame dragging plays a crucial role in this cosmic choreography. As the spinning object twists space-time around it, it forces magnetic fields in the surrounding disk to align with its rotation, channeling energy into narrow beams that pierce the darkness like cosmic lighthouses. The discovery and confirmation of frame dragging revealed space-time to be even more dynamic and alive than previously imagined. It doesn't just bend and stretch, it spins, swirls and flows. Planets twist it gently, stars twist it more dramatically, and black holes create cosmic hurricanes of pure geometry. Every rotation, from the spin of a child's toy to the whirl of an entire galaxy, leaves its fingerprint on the fabric of space-time, linking the dance of atoms to the rotation of stars. There's something profoundly beautiful about realizing that nothing spins alone. Every movement stirs the cosmic fabric just a little, creating gentle currents that connect the motion of everything from subatomic particles to galactic clusters. The universe is not indifferent. It feels the motion of everything within it, responding with quiet grace to each turn and twist. So the next time you picture the universe, don't imagine it as a still void punctuated by moving objects. Instead, envision it as a vast, viscous sea with gentle currents swirling where planets turn and immense vortices twisting where black holes spin. From the smallest rotation to the grandest galactic swirl, space-time flows with it all, a silent ocean stirred by gravity's patient hand. And perhaps most remarkably, this same cosmic fabric that bends, stretches, ripples, and swirls has become so integral to our daily lives that we carry its effects in our pockets, quietly negotiating with Einstein's equations every time we ask our phones the simple question, "Where am I?" So the next time you picture the universe, don't imagine it as a still void punctuated by moving objects. Instead, envision it as a vast, viscous sea with gentle currents swirling where planets turn and immense vortices twisting where black holes spin. From the smallest rotation to the grandest galactic swirl, space-time flows with it all, a silent ocean stirred by gravity's patient hand. And perhaps most remarkably, this same cosmic fabric that bends, stretches, ripples, and swirls has become so integral to our daily lives that we carry its effects in our pockets, quietly negotiating with Einstein's equations every time we ask our phones the simple question, "Where am I?" Most of us move through our days without thinking about Einstein, yet every time you check your phone for directions, you're relying on his profound insights about curved space-time to guide you safely home. That cheerful voice telling you to turn left in 200 meters represents one of the most extraordinary technological achievements in human history, a system that would be completely useless without constant corrections. For the way gravity bends space and time, without these relativistic adjustments, your GPS would be wrong by several kilometers within a single day, leaving you hopelessly lost in a world where your phone insists you're driving through buildings or floating in nearby rivers. The quiet truth is that modern civilization runs on curved space-time, even though most of us never pause to notice this extraordinary fact. Behind every successful navigation, every precisely timed financial transaction, every synchronized communication across continents, lies a continuous conversation between human technology and the geometric principles that govern the cosmos. To understand how Einstein's seemingly abstract theories became essential to finding your way through the world, it helps to know what GPS really is beneath its user-friendly surface. The Global Positioning System is a constellation of at least 30 satellites orbiting roughly 20,000 kilometers above Earth's surface, each one carrying atomic clocks so precise they would lose or gain less than a billionth of a second per day if left undisturbed. These timepieces are among the most accurate instruments ever created, counting the vibrations of cesium atoms with such steadiness that they could keep perfect time for millions of years. From their lofty orbital dance, these satellites continuously broadcast time signals toward the surface like cosmic lighthouses marking the passage of moments with extraordinary precision. Your phone receives those signals from several satellites simultaneously and performs what seems like a simple calculation. By measuring how long each signal took to reach you, it determines your exact position on Earth's surface. The principle sounds straightforward, but it depends entirely on synchronized timing across vast distances and varying gravitational fields. And here's where Einstein's insights become indispensable. Those satellites racing overhead experience relativity's effects in two distinct and competing ways, creating a delicate temporal ballet that engineers must choreograph with mathematical precision. First, the satellites are moving at tremendous speeds, about 14,000 kilometers per hour, which means their clocks experience what Einstein called special relativity. Time for them ticks slightly slower than for someone standing motionless on Earth's surface by about 7 microseconds per day. It's the same effect that would make a space traveler age more slowly during a high-speed journey to distant stars, just scaled down to the gentler velocities of orbital mechanics. But simultaneously, these satellites orbit far above Earth's surface, placing them in a weaker gravitational field than we experience down in the valleys and plains where we live our lives. According to general relativity, this makes their clocks tick faster than ours by about 45 microseconds per day. The two effects pull in opposite directions, special relativity slowing their time while general relativity speeds it up, but they don't cancel perfectly. The net result is that satellite time gains about 38 microseconds every 24 hours compared to time as measured on Earth's surface. That difference might sound trivial, a mere whisper in the grand symphony of time. But when you multiply it by the speed of light, the rate at which GPS signals travel, it becomes enormous. About 11 kilometers of error per day, growing larger with each passing hour. If engineers ignored Einstein's corrections, GPS would be worse than useless for navigation. Within a week, it would confidently inform you that your car was floating in a nearby lake, or that your morning walk had somehow carried you to the next town over. So before each satellite is launched, its atomic clocks are carefully set to tick slightly slower than their Earthbound counterparts, precisely offsetting the relativistic effects they'll experience once they reach orbit. As they circle the planet in their precisely choreographed dance, their time flows in apparent harmony with ours, not because time itself is uniform across different gravitational fields, but because the differences have been calculated and compensated for with extraordinary precision. It's a quiet treaty with space-time, signed anew every second. This means that every time your phone pinpoints your location, it's performing a small miracle of relativistic negotiation. Your device consults with satellites racing thousands of kilometers overhead, each one correcting for gravitational curvature, orbital velocity, and signal delay. Each location represents a gentle conversation between everyday life and the geometry of the cosmos, whispered 1 microsecond at a time through the mathematical language Einstein first wrote down over a century ago. It's not just navigation that depends on this cosmic precision. Modern banking systems use GPS time to timestamp financial transactions down to millionths of a second, ensuring that trades across different continents can be properly ordered and verified. The Internet's backbone relies on synchronized clocks to manage the flow of information through fiber optic cables spanning oceans. Communication networks, power grids, and scientific instruments all depend on the same relativistic corrections that keep your map app honest. Even more remarkably, as our clocks become increasingly precise, now measuring time down to quintillionths of a second, we're beginning to use them not just to navigate through space, but to map gravity itself. Differences in the rate at which time flows can reveal subtle changes in Earth's gravitational field, helping scientists study groundwater movement, volcanic activity, and the melting of ice sheets. This new field, called relativistic geodesy, turns the planet into its own instrument, listening to the quiet variations in time's rhythm to understand how mass moves. Beneath our feet, there's something profoundly moving about discovering that a theory born from pure curiosity about the nature of reality has become quietly essential to the functioning of our technological world. Einstein wasn't trying to improve navigation systems or enable global commerce when he puzzled over the equivalence of acceleration and gravity in that small patent office in Switzerland. He was simply trying to understand how the universe works, driven by nothing more than wonder and the belief that nature's deepest truths should be both beautiful and comprehensible. Yet his insights now run silently beneath nearly everything we do in our connected world. Every text message, every video call, every online purchase depends on networks synchronized by atomic clocks that honor Einstein's equations. The same principles that govern the grand dance of galaxies also dictate the precise timing of a signal from a satellite to your hand, creating an invisible web of relativistic corrections that keeps our modern world coherent and connected. So, the next time your phone pings with a location, notification, or guides you through an unfamiliar neighborhood, take a moment to appreciate the invisible physics humming beneath your fingertips. Behind that glowing screen lies a symphony of satellites, lasers, and atoms, all keeping time together on a curved planet in a curved universe. Your phone doesn't just find your position, it reconciles you with the fabric of space-time itself, negotiating between your immediate needs and the geometric principles that govern everything, from falling apples to the expansion of the cosmos. And as we've learned to read these subtle signatures of curved space-time in everything from GPS satellites to gravitational waves, we've begun to glimpse something even more profound. The possibility that this local curvature we experience around planets and stars might be part of a much larger geometric pattern, a cosmic architecture that shapes the entire universe on scales so vast they dwarf even our grandest earthly constructions. And as we've learned to read these subtle signatures of curved space-time in everything from GPS satellites to gravitational waves, we've begun to glimpse something even more profound. The possibility that this local curvature we experience around planets and stars might be part of a much larger geometric pattern, a cosmic architecture that shapes the entire universe on scales so vast they dwarf even our grandest earthly constructions. When Einstein first revealed that gravity was the curvature of space-time, he gave us more than a new theory of physics. He offered a new way to imagine existence itself. Suddenly, space wasn't merely an empty stage where cosmic dramas unfolded. It became an active participant, bending and flexing in response to matter and energy, creating invisible landscapes that guide everything from the fall of autumn leaves to the dance of distant galaxies. But there's another layer to this geometric story, one that stretches beyond the local dips and valleys we've been exploring together. Just as space-time curves intimately around every massive object, creating the pockets of curvature that keep planets in their orbits and bend starlight on its journey, it can also curve globally across billions of light-years, giving shape to the universe as a unified whole. The difference between these two kinds of curvature, local and cosmic, represents one of the most subtle and beautiful ideas in modern cosmology, connecting the gentle bend around our sun to the grand architecture of everything that exists. Local curvature has become a familiar companion on our journey through Einstein's universe. It's the kind of bending that creates the gravitational wells around planets and stars, the dimples in space-time that guide orbital motion and cause time to flow at different rates. Around every massive object, from the smallest asteroid to the most supermassive black hole, space-time dips gently, forming local pockets of curvature like dewdrops on an infinite, translucent web. If you could somehow see this geometry directly, you might imagine a vast, flexible membrane bowing softly under the weight of each galaxy, each star creating its own tiny indentation that ripples through the surrounding fabric. But zoom out far enough, past individual solar systems, beyond galaxy clusters, across the cosmic web of filaments and voids, and a much grander question emerges. What is the overall shape of the universe itself? If you could somehow step outside the cosmos and observe it all at once, would the fabric of space appear curved like the surface of an enormous sphere? Would it stretch open like a saddle, curving outward forever? Or would it be perfectly flat, extending infinitely in all directions with no overall bend at all? Einstein's equations allow for all three possibilities, like three quiet melodies the universe could have chosen to play. Each represents a different cosmic geometry, and each carries profound implications for how the universe began, how it evolves, and how it might ultimately end. A closed universe would be like living on the surface of a vast sphere, finite but without boundaries or edges. Travel far enough in any direction, and in principle you could return to where you started, though such a journey might take longer than the age of the universe itself. In this geometry, parallel lines would eventually converge, and the angles of a triangle drawn between distant galaxies would add up to more than 180 degrees. An open universe, by contrast, would curve outward like the surface of a saddle, stretching infinitely in all directions. Here, parallel lines would gradually diverge, and cosmic triangles would have angles that sum to less than 180 degrees. Such a universe would expand forever, with galaxies drifting farther and farther apart until the stars burn out and the cosmos grows cold and empty, thinning into an eternal, silent darkness. Between these extremes lies the delicate possibility of a flat universe, balanced precisely on the knife's edge between closure and infinite expansion. In this geometry, parallel lines would remain parallel across cosmic distances. The angles of triangles would sum to exactly 180 degrees, and expansion would proceed at just the right rate to balance matter's inward pull against the universe's outward push. It's a cosmic Goldilocks problem played out across billions of light years. Too much matter and energy, and gravity eventually halts expansion, leading to a future collapse. Too little, and the universe expands forever, thinning into silence. Just right, and it expands gracefully without ever quite tearing itself apart. The remarkable thing about cosmic curvature is that for all the universe's complexity, its overall shape comes down to a single, crucial number, the total density of matter and energy it contains. If that density exceeds a certain critical value, space will curve closed. If it falls short, space will curve open. If it matches the critical density exactly, the universe will be perfectly flat. But how do you measure something as abstract as the curvature of all space when you can only observe from one small corner of existence? The answer lies in the oldest light in the universe, a faint whisper called the cosmic microwave background. This gentle radiation is the afterglow of the Big Bang itself, a snapshot of the cosmos when it was just 80,000 years old, still glowing with the warmth of creation, but finally cool enough for light to travel freely across space. This ancient radiance isn't perfectly smooth. It carries tiny fluctuations, slight variations in temperature and density that were the seeds from which all later structure grew. Every galaxy, every star, every planet that would ever form. These primordial patterns are exquisitely sensitive to the geometry of the space they crossed on their journey to us. If the universe were closed, light from distant regions would converge slightly as it traveled, making the patterns appear larger than their true size. If it were open, the light would diverge, making them appear smaller. But if the universe were flat, the patterns would appear at their natural scale, undistorted by cosmic curvature. By mapping these ancient temperature variations with extraordinary precision, Satellites like WMAP and Planck have effectively measured the curvature of the entire observable universe. What they found is both elegant and mysterious. On the largest scales we can observe, the universe appears astonishingly close to flat, with a margin of error less than 1%. This means that if you could draw a triangle with sides spanning billions of light years, its angles would add up to almost exactly 180 degrees. Space, it seems, barely curves at all when you look across the entire cosmos, but almost flat isn't. Quite the same as perfectly flat, and that subtle distinction could have profound implications we're only beginning to understand. Even a tiny curvature, too small to detect with current instruments, might reveal itself if we could somehow observe the universe on scales far larger than what our telescopes can reach. Perhaps space does curve gently back on itself, creating a cosmos so vast that its bend is imperceptible across the distances we can measure. This cosmic near-flatness also doesn't erase the local curvature we've been exploring throughout our journey. Galaxies still sit in their own gravitational dimples, stars still bend starlight along gentle curves, and black holes still twist space-time into whirlpools of pure geometry. The universe is flat on average, but richly textured in detail, smooth when viewed from the greatest distances, but filled with structure and curvature on smaller scales. It's like a vast ocean that appears mirror-smooth from an airplane, but reveals waves, currents, and eddies when you look more closely. The expansion of space itself adds another layer of wonder to this cosmic geometry. When astronomers speak of an expanding universe, they don't mean that galaxies are flying apart like fragments from an explosion. The forces that hold matter together, electromagnetism, nuclear forces, even local gravity, are far stronger than the gentle stretching of cosmic expansion. Instead, it's the space between distant galaxy clusters that grows, carrying them apart as the very fabric of reality stretches. Galaxies aren't racing through space. They're being carried apart because space itself is increasing, like dots painted on the surface of a slowly inflating balloon. This expansion happens everywhere at once, even in regions where space is nearly flat. From any galaxy's perspective, all others appear to be receding, yet no single location serves as the center. The universe expands democratically, honoring no special position, guided by the same geometric principles that govern local curvature, but operating on scales that encompass everything we can see and much that we cannot. If you could visualize this cosmic architecture, you might picture a vast, nearly flat grid stretching endlessly in all directions, dotted with bright knots where galaxies cluster together. Each knot sits in a small depression created by local gravity, while the overall grid remains gently curved, almost imperceptibly, arched across distances that challenge imagination itself. The universe reveals itself as both flat and curved, depending on how closely you look. Local curves giving rise to motion, structure, and the possibility of life itself, while global flatness allows the cosmos to endure, expanding gracefully rather than collapsing back on itself or tearing apart. This layered geometry creates a quiet balance that connects the smallest scales to the largest. Einstein's equations describe both the swirl of space-time around a black hole and the shape of everything that exists, weaving one continuous story that spans from the quantum realm to the cosmic horizon. In that story, we find ourselves not as separate observers peering out at a distant universe, but as participants in the same geometric symphony, our own atoms and heartbeats part of the curved space-time that guides the dance of galaxies across the night sky. And yet, for all its mathematical beauty, this geometric vision needed more than elegant equations to earn its place as our understanding of reality. Across more than a century, each prediction would need to face the ultimate test, the patient questioning of nature itself. Through experiments so delicate they could detect the universe's whispered confirmations, of Einstein's profound insights. And yet, for all its mathematical beauty, this geometric vision needed more than elegant equations to earn its place as our understanding of reality. Across more than a century, each prediction would need to face the ultimate test, the patient questioning of nature itself. Through experiments so delicate they could detect the universe's whispered confirmations of Einstein's profound insights. When Albert Einstein completed his general theory of relativity in 1915, it represented such a radical departure from everything that came before that even he carried quiet uncertainty about how it would withstand observation's gentle scrutiny. The mathematics was breathtaking, the concepts profound, yet beauty alone has never been enough to make a theory true. It needed to face the one judge that no idea, however brilliant, can avoid, the universe itself, speaking through the careful measurements of patient scientists. Einstein understood this deeply. His curved space-time wasn't merely poetic metaphor, but precise mathematical description, making specific predictions about how light would bend, how time would flow, and how objects would move through the cosmos. Over the following decades, each prediction would be tested with increasing precision, creating a quiet symphony of confirmation that transformed revolutionary theory into established fact. The first answer came from the sky during a rare midday twilight in May 1919, when the moon slipped across the sun and starlight emerged in the sudden darkness. Arthur Eddington's expeditions to Principe and Brazil carried photographic equipment designed to capture those precious moments of totality. When the plates were developed, they revealed exactly what Einstein had predicted. Stars near the sun's edge appeared shifted outward by 1 3/4 arc seconds, their ancient light deflected by the sun's curved geometry. It was a whisper of an angle, yet precise in its agreement with Einstein's calculations. Newspapers proclaimed lights all askew in the heavens, but the deeper truth was gentler. Light honors the shape of space, tracing cosmic curves with tireless fidelity. The second confirmation emerged from Mercury's long-standing puzzle. For decades, astronomers had noticed that the innermost planet's elliptical orbit wasn't quite closing in on itself, with its point of closest approach creeping forward by 43 arc-seconds per century after all known gravitational influences were accounted for. Einstein's equations explained this tiny remainder perfectly, showing Mercury faithfully following its geodesic through the sun's intense curvature, where geometry itself twisted slightly with each orbit. No mysterious force was needed, just space-time's natural response to concentrated mass. Time itself provided the third, gentle confirmation through gravitational redshift. In 1959, physicists Robert Pound and Glenn Rebka conducted an experiment of extraordinary delicacy in a Harvard University tower, measuring how gamma rays changed frequency as they traveled between floors. The effect was minuscule, less than 1 part in 100 trillion, yet their instruments detected exactly the shift Einstein's equations predicted. Light climbing out of Earth's gravitational well-lost energy precisely as relativity demanded, carrying news of time's variable tempo in its stretched wavelength. The fourth classical test arrived through radar's patient echoes. Erwin Shapiro realized that if space-time were truly curved, radio signals passing near the sun would take slightly longer to complete their journey than they would through flat space. When he bounced radar beams off planets and measured their return, they arrived with precisely the delay Einstein's geometry required, a courteous hesitation in the presence of the sun's curvature. As technology advanced, these confirmations became increasingly precise and creative. Atomic clocks, our most faithful timekeepers, grew sensitive enough to detect gravity's adjustments over a flight, a mountain climb, even a few floors of elevation. Identical clocks separated by modest heights ticked at measurably different rates, time itself responding to altitude with tenderness you could quantify. GPS satellites became inadvertent laboratories, their synchronized timing possible only because engineers continuously negotiated with Einstein's equations. offsetting the slowdowns of speed against the speed-ups of weaker gravity. Spacecraft extended these tests across the solar system. The Cassini mission orbiting Saturn used radio signals to measure light bending near the Sun with parts per 100,000 precision. Gravity probe B watched gyroscopes drift by tiny amounts as Earth's rotation gently stirred spacetime, confirming that the cosmic fabric doesn't merely curve, it can be twisted by spinning mass. Then, a century after the first predictions, spacetime raised its voice just enough for human ears to hear. In September 2015, LIGO's arms stretched and compressed by less than 1,000th of a proton's width, recording the final dance of two distant black holes as a rising chirp lasting 0.2 of a second. The signal matched Einstein's equations not just in pitch and rhythm, but in every detail: masses, spins, the final ring-down of merger. Soon after, neutron stars collided and announced themselves in multiple messengers, first as gravitational waves, then as gamma rays, optical light, and radio emissions. The universe had learned to speak in harmony. Even our pictures began to agree. The Event Horizon Telescope, weaving radio dishes across the globe into one Earth-sized eye, revealed the shadow of a supermassive black hole, its luminous ring skewed by motion and gravity exactly as simulations predicted. For the first time, humanity glimpsed the silhouette of curved spacetime at its most extreme. Through all these tests, no decisive contradiction has appeared. Each experiment, from falling towers to orbiting clocks, from radar echoes to rippling lasers, has tightened the embrace between mathematics and observation. General relativity remains one of the most thoroughly verified theories in science, flexible, predictive, and astonishingly accurate wherever we can measure. Yet physicists carry gentle unease alongside this confidence. The same equations that guide planets and predict eclipses encounter infinities in black hole interiors and at the universe's first instant, where quantum effects can no longer be ignored. Two masterworks, Relativity's smooth geometry and quantum mechanics' probabilistic shimmer, stand side by side, each undefeated in its domain, each asking the other to translate their different languages into a unified voice. So the testing continues, not from doubt but from hope. New instruments listen for whispers that don't fit the familiar rhythm, clues that might lead us to where the smooth and the granular finally meet, where geometry and quantum uncertainty discover they're part of the same deeper design. So the testing continues, not from doubt but from hope. New instruments listen for whispers that don't fit the familiar rhythm, clues that might lead us to where the smooth and the granular finally meet, where geometry and quantum uncertainty discover they're part of the same deeper design. For more than a century, two magnificent theories have described our universe with breathtaking success, yet they speak in languages that seem impossible to translate. General relativity governs the vast and stately, where planets trace their patient orbits and galaxies bend ancient starlight across billions of years. Quantum mechanics rules the minute and restless, where particles flicker into existence like fireflies and uncertainty becomes the only certainty we can trust. Each theory works flawlessly within its own domain, like two master musicians playing different instruments in perfect tune with their respective symphonies. But at the edges of understanding, where gravity becomes intense and distances shrink toward the unimaginably small, their melodies begin to clash in ways that hint at a deeper harmony we haven't yet learned to hear. Einstein's curved spacetime gives us a universe of smooth, continuous geometry where every bend and ripple can be precisely mapped. It's a world of silk-like fabric responding gracefully to the presence of mass and energy, creating the gentle valleys that guide planets and the subtle slopes that slow the passage of time. Quantum mechanics, by contrast, reveals reality as fundamentally granular and probabilistic. Energy arrives in discrete packets, particles exist in multiple states simultaneously, and the very act of observation can collapse infinite possibilities into a single, definite outcome. The trouble begins when we ask both theories to describe the same extraordinary places. Imagine zooming into space-time far beyond what any microscope could achieve, past atoms and protons down to the Planck scale, about 10 to the minus 35 meters, roughly 100 billion times smaller than a proton. At that extraordinary scale, according to most physicists, the smooth curves of Einstein's geometry might give way to something chaotic and alive with fluctuations. Space itself could foam and bubble like water at a violent boil, with tiny regions of space-time constantly appearing and disappearing in quantum uncertainty. Two cosmic theaters demand this impossible translation. One is the heart of a black hole, where enormous mass compresses into an unimaginably tiny volume. Einstein's equations predict that space-time funnels to a singularity where density becomes infinite, a mathematical impossibility that signals the breakdown of our current understanding. The other is the universe's first instant, when all of space was compressed into something smaller than the smallest thing we can imagine, hotter than hot, where quantum fluctuations would have jostled the same geometry that drove cosmic expansion. Physicists have spent decades mapping possible routes across this frontier, and several elegant approaches have emerged, each offering its own translation between the quantum and the cosmic. String theory suggests that reality's fundamental ingredients aren't point-like particles, but tiny vibrating strings so small they exist at the very edge of imagination. Different modes of vibration become the particles we observe, electrons dancing one rhythm, quarks another, gravitons carrying gravity's gentle tune. In this vision, space-time and matter arise from the same underlying music, naturally unifying all forces but requiring extra dimensions curled so tightly we cannot detect them. Loop quantum gravity takes a different path, proposing that space itself is woven from finite loops of energy, forming an intricate network where distances and areas come in discrete steps like pixels on a cosmic screen. From afar, these quantum threads blend into the smooth fabric of Einstein's equations, but up close, the weave becomes visible. Space becomes digital rather than analog, with a smallest possible unit that cannot be subdivided further. Even more radical ideas suggest that space-time itself isn't fundamental but emerges from something deeper, perhaps from networks of quantum information, invisible relationships that create the illusion of geometry when viewed from a distance. In this picture, space and time might be collective phenomena, like temperature arising from molecular motion, with Einstein's elegant curves becoming the large-scale shadow of quantum correlations we're only beginning to understand. The holographic principle adds another layer of mystery, proposing that everything inside a region could be fully described by information encoded on its boundary, like a cosmic hologram projecting three-dimensional reality from a two-dimensional surface. If true, our entire universe might be a kind of projection, with geometry emerging from the mathematics of information itself. Each approach offers glimpses of the same elusive goal, a world where quantum uncertainty and gravitational curvature are not enemies but partners in describing reality's deepest layer. Yet none has claimed the final word, and perhaps none captures the complete story. The scales where quantum gravity becomes important are almost impossibly remote from direct experiment. Even our most energetic particle accelerators barely scratch the surface of these fundamental realms. Still, hints whisper from unexpected places. Black holes seem to connect geometry, thermodynamics, and quantum information in mysterious ways. Hawking's discovery that they emit faint radiation suggests these cosmic sculptures aren't truly black, but glow with quantum light, slowly returning their borrowed energy to the cosmos. Recent studies of quantum entanglement reveal patterns that seem to reconstruct spacetime's geometry itself. as if space grows from relationships rather than existing independently. There's something profoundly beautiful about living in this twilight between two masterpieces of understanding. The universe behaves with smooth elegance on grand scales, while whispering of something granular and uncertain in its foundations. Every orbiting planet and every quantum experiment participates in the same cosmic puzzle, waiting for the moment when the large and small finally recognize each other as aspects of the same deeper truth. Until that recognition comes, we rest in the gentle embrace of mysteries that remain beautiful precisely because they're unfinished. The search continues in laboratories and observatories, in mathematical abstractions and computer simulations, all seeking the hidden harmony where Einstein's curves and quantum uncertainty finally learn to sing together. And when they do, they might reveal not just how the universe works, but why it chose to express itself through the particular combination of geometry, energy, and information that allows curious minds like ours to contemplate existence itself. The cosmos, patient, as always, keeps its deepest secrets while inviting us to listen more carefully to the quiet music playing at the intersection of the vast and the minute, where the next chapter of understanding waits to unfold like a gentle dawn across the landscape of knowledge. The cosmos, patient, as always, keeps its deepest secrets while inviting us to listen more carefully to the quiet music playing at the intersection of the vast and the minute, where the next chapter of understanding waits to unfold like a gentle dawn across the landscape of knowledge. Tonight, we've followed a simple idea to its quiet horizon, discovering something both profound and surprisingly gentle. Matter writes the map of reality, and motion reads it with perfect fluency. Planets, photons, and people don't need to be told what to do. They glide naturally along the shapes already inscribed in the fabric of space and time, following paths so elegant they feel less like physics and more like poetry, written in the language of geometry itself. Gravity, we've learned, isn't a mysterious tug pulling objects through emptiness, but a pattern woven into the very structure of existence. It's the gentle curvature that guides every step you take and every beam of starlight crossing the cosmos, creating invisible landscapes where motion becomes the art of taking the straightest possible path through a curved reality. Once you see it this way, the universe feels less like a collection of forces competing for control, and more like a vast river system where everything flows according to the same patient logic. Return for a moment to that river we imagined at the beginning of our journey together. The water doesn't argue with the valley's shape or struggle against the contours carved by time and weather. It simply flows where the landscape allows, finding its way through the terrain with effortless grace. So it is with everything that moves through space-time. Starlight flows along invisible bends, skimming past suns and arcing around massive clusters, braiding faintly through the cosmic web. Planets drift like leaf boats on that same current, their orbits not forced by invisible chains, but permitted by the gentle geometry that mass and energy have written into the fabric of reality. Even time enters this flowing stream, running a little slower where mass gathers in dense concentrations, quickening where space opens into the emptier regions between worlds. To notice this is to trade drama for clarity, to find deeper wonder in the quiet precision of natural law than in any imagined cosmic struggle. The beauty lies in how profoundly democratic these principles are. A clock on a mountaintop, a satellite in orbit, a photon leaving a distant star, each following the same gentle rule with perfect consistency. Think back to Einstein's falling elevator, where weightlessness revealed itself as perfect freedom to follow spacetime's natural curves. Remember Mercury's patient precession, tracing the sun's twisted geometry with exquisite precision. Recall that moment in 1919 when starlight bent around the eclipse-darkened sun, confirming that even light honors the shape of space. Consider the gravitational waves that reached LIGO's arms after traveling 1 billion years, carrying news of black holes dancing their final dance. Each discovery revealed the same underlying truth. The universe prefers gentleness where we expected severity, invitation where we imagined command. Your phone's GPS system quietly negotiates with these same principles every moment, correcting for time's variable flow as satellites race overhead in weaker gravity. The differences we observe, from the smallest tick of an atomic clock to the grand spiral of entire galaxies, are variations on the same fundamental theme. Curvature guides motion. Motion reveals curvature. And the cosmos keeps its own time with extraordinary patience, never rushing, always flowing according to the deepest mathematical harmonies. It's comforting to realize that nothing in this vast universe relies on haste or struggle. Geometry is calm by nature, never demanding attention but always rewarding it, like constellations emerging slowly as your eyes adjust to deepening darkness. There are no sharp commands in Einstein's universe, only soft constraints and gentle invitations. The cosmos doesn't insist on any particular outcome. It simply offers the most natural paths and allows everything to choose the route that flows most easily through the four-dimensional landscape of space and time, even as mysteries remain the marriage of quantum uncertainty with cosmic curvature, the true nature of dark energy. The universe's ultimate geometric destiny. They wait patiently for future generations to listen more carefully to space-time's whispered secrets. But tonight, these questions can drift gently into the background, becoming part of the cosmic hum that surrounds all understanding. Somewhere above you right now, starlight continues traveling those gentle curves we've explored together, each photon following its geodesic with tireless dedication across distances that dwarf human comprehension. Somewhere, in the depths of space, entire galaxies are reading the same geometric map that guides the moon's path across our own small sky, all participating in the same universal dance of matter, energy, and curved space-time. Before you allow sleep to carry you along its own natural current, remember that you've spent these quiet moments exploring one of humanity's most profound discoveries. The recognition that we live not in a universe of mysterious forces, but in a cosmos of elegant geometry where everything follows the same beautiful principles. If this gentle journey has helped you unwind from the day's sharper edges, perhaps you'd consider subscribing to The Whispering Scientist for more calm explorations of the cosmos. Your quiet presence here makes these nocturnal voyages possible, connecting minds across continents in the same spirit of wonder that has guided human curiosity from ancient stargazers to modern gravitational wave detectors. For those already part of this gentle community, thank you for sharing these moments of cosmic contemplation. If you'd like a soft notification when the next journey begins, that little bell will ensure the river of understanding can find you again. Now let the edges of today soften and blur like watercolors in gentle rain. Let the ideas we've shared loosen their grip and settle like cosmic dust in a quiet corner of awareness. The map of curved space-time will still be here in the morning, its principles still true, its curves still kind to everything that moves through them. Light will continue its patient journey along invisible geodesics. Planets will keep falling perfectly around their stars, and time will maintain its unhurried drift through the valleys and peaks of gravitational landscape. You don't need to hold on to any of it actively. The universe breathes quietly around you, expanding gently, curving softly, singing its gravitational songs in frequencies too low for conscious hearing, but perfectly tuned for dreams. Space and time cradle everything with geometric tenderness, and in that embrace, even the most restless mind can find its own natural path toward rest. Sleep well beneath the curve of space-time itself, knowing that you're part of the same elegant fabric that guides distant galaxies and governs the dance of atoms in your own gentle breathing. The river flows on, patient and eternal, carrying all things toward their most natural destinations, with the same grace that has shaped the cosmos since light first began its endless journey through the curved geography of existence itself. Good night.